So today we are going to start looking at forces that go in two directions. So up until this point, we focused our energy purely on objects that are moving only in the horizontal direction or only in the vertical direction, or that only have forces applied in the horizontal or the vertical direction. Now we're going to take a look at forces that are applied at an angle, okay? Because that's much more real life, is that we have things that are being pulled upward at an angle or pushed at an angle or whatever it might be, but it's got some angle component to it. So when we solve force problems with multiple directions, we have to break them into components. Okay, we already know how to do this because we did it with our projectile motion. Okay? Oops. Sorry. All right. When we start looking at these forces that are in two dimensions, it might look something like this. Right? We've got an object. It's being pulled with a force of, 30 newtons at 25 degrees, right? And so if I'm looking at that force, it doesn't give me purely y and purely x. It's at an angle. And we know that we have to break those vectors into their components. So we would break it into force y and force x, and I'll talk about that here in just a little bit. But we want to be able to find out what's the value of just the y component of that force and what's the value of just the x component. And then we'll go through and start solving the problem just like we know how, and taking the positive forces minus negative forces, either in the x or the y direction, whatever we need to solve our problem. Does that make sense? So that's the only really addition we're making in this section of notes, is that instead of forces being applied purely vertical or purely horizontal, now they're being applied at an angle, and so we've got one extra step to break them into x and y. Okay, so we're just going to jump right in here as an example, and we'll start working through this together. Okay, a force, I'm going to give you a few minutes to write down what you need, and then we'll start through it together. Okay, so it says a force of 2,000 newtons acting at an angle of 60 degrees to the horizontal is exerted on a towed car. The car is accelerated from rest at a rate of 10 meters per second squared. Find the mass of the car. Okay, so go ahead and get written down what you need to, and then we're going to start with the free body diagram here in just a minute. All right, so free body diagram of my car here. What do we always have acting? All right, so for the free body diagram, we said we have gravity, Fg. It's on a surface. We have a normal force. And then we've got the car that's being towed at an angle from 60 degrees to the horizontal. So all that means is that my angle is 60 degrees right here. Right? Because there's my horizontal. If I would go up 60 degrees, that's where that force would lead me to. Okay? So from the horizontal just means you go horizontal and you go up 60 degrees. Okay? And then it asks, it tells us we're pulling with a force of 2,000 newtons. Okay? And so what would we call that towing force? F what? Net. F net. No, because that would be the overall. Okay, so towing force, it's specifically the towing force that's exerting 2,000 newtons. So we could call it Ft for tension, or we could call it F applied because we're pulling on that object. I usually just like to keep it as F applied, but you could put it as Ft for tension since it involves a rope or a cable also. That's fine. Okay, so let's go ahead and say we do call it Ft. What would this side of my triangle then be called? F, T, Y, and force of tension in the x direction on the bottom, right? Force of tension in the y direction, force of tension in the x direction. Or you could call them F applied x and F applied y. Doesn't really matter what the name of it is. Okay. It tells us the car is accelerated from rest at a rate of 10 meters per second squared. Do you think that's a vertical acceleration or a horizontal acceleration? Think about when a car is towed. Is it moving horizontally or vertically? horizontally. So this has to be horizontal acceleration, which means when I go to set up my net force equation, am I focusing on horizontal or vertical forces? Horizontal, right? I want to be looking only at horizontal forces. And so how many of them are there? How many horizontal forces do we have? Just one, right? There's only one horizontal force. It doesn't tell us anything about friction, so we can ignore friction. So when I go to set up my F net equation, I'm going to focus just on the horizontal forces, which would be F tension in the x direction minus 0, right? There's nothing opposing that force that we know of. You don't have to put the minus 0. I just like to put it so I know that I thought about it and I know there's nothing opposing it, right? That's the only reason I like to make sure I do that. So our goal is to solve for the mass of the car. Can we solve FTX? Can we know the x component of that force? Yes, using sine, cosine, or tangent. So if that's the adjacent side, I'm going to take 2,000 times cosine of my angle, 2,000 times cosine of 60, and I get a force of 1,000 newtons. Right? To solve for FTX, I get 1,000 newtons by doing 2,000 times cosine of 60. Okay? And so now I go to look at this. I'm going to say 1,000 minus 0. Ooh, I keep trying to zoom in. What can I substitute here for F net? What'd you say? Good. Mass times acceleration equals that. And so if I go to solve for the mass of my car, that means I get a mass of 100 kilograms. Okay. Hey, what questions do we have about that problem? We didn't need to bother solving vertical forces because my acceleration of my car had to have been horizontal. Right? So there wasn't any reason for us to really spend time with the vertical forces because they are evaluated completely separately. Right? They're independent of one another. So there was no need for us to go solve for FTY. It's not a bad practice to just solve them both immediately, but we just didn't need to in this case. All right. Let's try this one. A 50-kilogram washing machine is being lifted upward with a force of 200 newtons at an angle of 40 degrees to the horizontal. The machine begins to slide. Find the normal force acting on the washing machine. Okay. So here's my free body diagram of my washing machine. I've got gravity. It says we're lifting it or we're pulling it upward at 40 degrees. My force that I'm pulling with is 200. And then I also have a normal force because it's on a surface. So, oh, that's kind of lagging there. Sorry. I actually did draw it. It's just not showing up on your screen. What's the significance of this sentence? The machine begins to slide. What's the significance of that? What did you say? Yeah, it's moving horizontally. Exactly. So what's happening is they're lifting it like this. But it's still moving just horizontally. It's not moving vertically. So that's really important. Even though it says lifting, it's still got only horizontal motion. So that's really important. So that means if we're looking at normal force, that's what we want to end up finding, normal force. If we're looking at the normal force, which is vertical, what do we know then about the net force in the vertical direction? Okay, if we set our washing machines only moving horizontally, what does our net force in the vertical direction have to equal? 0, right? Because it won't be moving in the vertical direction. More specifically, it won't be accelerating in the vertical direction. So let's start looking at that. First of all, the normal force, is it vertical or horizontal? It's vertical. So I'm going to go ahead and circle all of the vertical forces that I have, because we have to account for all of those vertical forces in our problem. Right? In our net force equation, we have to account for all 3 of them. And so when we look at our angled force, we don't care about the 200. We won't use the 200 in any problem. What we need to use more is F applied Y. Okay? F applied Y is what we're really going to need. Okay? We don't need the 200. We just need the Y component of that 200. So if I was going to solve for F applied Y, I would take 200 times sine of 40. And I get 128.6. Okay, 128.6 newtons. And so now as I go to look at my net force equation, like we said, we've got 3 vertical forces, 1, 2, 3, all that we have to take into account. So I would say F net equals, what are my upward forces here? Normal, what else? F applied Y, and then what's my downward force? Fg, right? Gravitational force. All right, we know that normal force is what we're solving for. Okay, so I'm going to leave that alone. Fn plus F applied Y, which we know is 128.6. And then how do we know Fg? Okay, not just 9.8. Fg equals mass times 9.8. So we need to take 50 times 9.8, and we get 490 newtons. Right? So now I'm going to go back here and plug in minus 490. Okay, and then we said, what's the net force in the vertical direction here? Yeah, we talked about it. It's 0 because it's not, our object's not moving in the vertical direction. And the net force equals 0 when my object is at rest or if it's moving at constant velocity. So my net force is 0. Okay, if it helps you to say F net Y, you can do that just so you know you're focusing only on vertical components. You don't have to, but you could if you wanted. Okay, so now I'm just going to combine my like terms. 128.6 minus 490 gives me Fn minus 361.4. I'll add that to the other side, and I just get Fn equals 361.4 newtons. Okay, do you remember what we talked about? What would happen if my normal force came out negative? Is that a possible scenario for a normal force? Could my normal force come out negative? What do you think? If I had a negative normal force, that means the force would be pointing in the downward direction, which wouldn't be opposing gravity. Right? If I had a negative normal force, that means that whatever other positive force I had, like that one, whatever positive force I had would be greater than gravity, which means my object would no longer be on the surface. Right? It would have been picked up. So let's say this one, for example, was 500. Let's say my F applied Y had been 500. That means this would have come out at 500 minus 490, which means I applied more lifting force than gravity was applying, which means my object would have been moved off the table, right? So I wouldn't have had a normal force. So if your normal force does come out negative, that's a clue that you've got a greater applied force than gravity, and so now your object's no longer on the table, which means you just don't have a normal force. Right? That's how you would answer that. Don't have a normal force. What about which one?
Like, if it came out positive, it's still
we want normal force to come out positive because it's pointing upward. Right? So this is good. An 84 kilogram sled is being pulled with a force of 40 newtons at an angle of 33 degrees from the horizontal. What's the normal force and what's the horizontal acceleration? So we have two different things that we're looking for here. Okay, in this scenario, are we going to need both our F applied X and F applied Y? Are we going to need both of them? I think so. Because we're going to need normal force, which is vertical, and we're going to need horizontal acceleration, which is horizontal. So we're eventually going to need both of them. So let's go ahead and just solve for both of them now. That way we have them. Okay? F applied X would be 40 times cosine of 33. F applied Y would be 40 times sine of 33. Why don't you guys go ahead and solve those? $33.5 and 21.8. Is that about what you had? Okay. One more thing here from our free body diagram that we can solve ahead of time. What is it? FG. FG we know is mass times 9.8. And so that gives me 823.2 newtons. Okay, and we don't know what the normal force is. That's what we're solving for. So it doesn't matter which one of these we solve first because they're independent of one another. So let's just go ahead and solve for normal force first. Okay, so normal force is y direction. If I'm looking at my net force in the y direction, let's look at how many vertical forces do I have. I have 1, 2, 3. Agreed? Right? Normal force plus F applied Y minus gravity. Okay. Any question about how we set up that net force equation? Right? 2 positive forces, 1 negative force. What do we know about my F net value in the vertical direction? It's 0, right? Because my sled is being pulled. Right? My sled is being pulled on the ground. So my net force is 0. Normal force we're solving for. F applied Y is 21.8. And FG is 823.2. Okay? And so we get a normal force equal to 801.4 newtons. Agreed? Right? 801.4 newtons. So you would see, like, if there was nothing else happening in the vertical direction, my normal force would have been 823.2, right? It would have been exactly opposite of gravity. But since we were pulling upward on our object, right, pulling upward and sliding, we were removing some of the work that the normal force needed to do. So our normal force was less than it needed to be, okay? Or less than it usually would have been. All right, horizontal acceleration now. How many forces do we have in the x direction? Just one. Just F applied x, right? It didn't say anything about friction, so F applied x is the only force we have in the horizontal direction. So as I start plugging that in, I would say F net equals force applied x. And then I like to just go ahead and put minus 0 so I know I thought about it. There's nothing else there. There's no other forces acting, but there's nothing there, okay? So now it asks me to solve for horizontal acceleration. How can I get to a point where I've got acceleration in my equation? Right, I substitute for F net m times a. I'm going to move over here to the side so I got a little bit more room. M times a equals F applied x. And so now I'm going to start plugging in the numbers. 84 times a equals 33.5. And which way would I divide over? Do I divide by 33.5? I divide by 84. Right? I need to move that over to the correct side. 33.5 divided by 84 gives me an acceleration of 0.4 meters per second squared. All right, I'm going to draw. Actually, we're just going to do this one together because this one's one we haven't seen before yet. That's what the system looks like. A 7,000 kilogram wrecking ball is at the end of the cable. In the middle of the cable is another ball with a mass of 1,200. If the crane is lowering the system at 2.1 meters per second squared, what's the tension in each of the sections of cable? So we're looking at what's the tension here and what's the tension here. Okay. We're going to look at what's happening in these cables individually, okay? And we can kind of ignore the mass of the cable itself. We're just looking at the mass of the object. And so let's look at the top one first. If I was going to draw a free body diagram for this tension, this cable right here, I would say gravity is pulling us down, and tension in the cable is pulling us upward. Okay, it's coming, but there we go, right? We've got gravity that's pulling us down and then tension that's pulling us upward. Would we agree with that? It's a pretty simple scenario, but we've just got to think about a couple different things. So when we're looking at this object and I'm taking my net force equation, F net equals tension minus gravity, the thing I have to pay attention to is that the gravitational force that's pulling it down has to account for all of the mass that hangs below it. All of the mass that hangs below it. So in this system, and we're looking at the top cable, how much mass are we really talking about? Are we just talking about 1,200 kilograms? We're talking about 1,200 plus 7,000. So in our scenarios, Fg is really 8,200 times 9.8, right? Ft is what we're solving for. And F net, we're going to say mass times the acceleration, which the acceleration was given, but there's an important part here that we have to look at. It says it's lowering. It's lowering with an acceleration. That means our acceleration is negative 2.10. Okay? Anytime something is being lowered with an acceleration, it's got to be a negative acceleration. Okay? Now we just go ahead and solve for Ft. So 8,200 times 2.10 is negative 17,220 equals Ft minus Fg. And so I'll add that to the other side. And that gives me a value of 63,140 newtons equals Ft. 63,140 newtons is the tension in that part of the cable. Okay? So now if we look at the middle section of cable, our free body diagram actually looks exactly the same, except the mass that's hanging below it is not near as much, right? The mass that's hanging below that part of it is only 7,000. So if I'm looking at this part of my cable, I would say FG, FT. My net force equation would look almost identical. Except for mass, we don't have to use all of the mass, we just use what hangs below it. So 7,000 times negative 2.1 equals FT minus 7,000 times 9.8. All right, so go ahead and solve that and solve for FT. So the tension in this part of the cable was 53,900 newtons.